Depending on the difference in electronegativity, the sharing of electrons in a covalent bond is not going to be equal. The shared electrons will be shifted a little bit towards the more electronegative atom, leaving the less electronegative atom with less amount of electron cloud. And as a result, the more electronegative atom will be electron rich, or will have more electron cloud localized on it, that can be represented with a delta negative charge on it. And the less electronegative atom is going to have less electron density, or will exhibit partial positive charge on it. That situation, when you have an object with a partial negative end and a partial positive end, is called a dipole moment. So in this case, the bond is going to be electrically a dipole moment, and it's usually represented with an arrow that looks like this, pointing towards the negative end of the molecule. The magnitude of the dipole moment that will form in this case is going to depend on the electronegativity difference as well as the length of the bond. So the more electronegativity difference in case of hydrogen fluoride is going to result in a larger dipole moment in comparison to the less electronegativity difference in case of hydrogen iodide. So we learned how a certain bond could be polar, but in order for a molecule to be polar, it should have an overall dipole moment. This is not going to be possible if you have a symmetrical molecule. For example, if you have a linear molecule that has polar bonds, the first bond is going to have a dipole moment that runs along this direction, and the second bond is going to have dipole moment of the same magnitude running into the exact opposite direction. And as a result, they will cancel each other, and the molecule will have a zero overall dipole moment and become nonpolar. Same case will happen if you have any symmetrical molecule. Any of the symmetrical shapes, linear, trigonal, planar, tetrahedral, trigonal bipyramidal, and octahedral. So for a trigonal planar, for example, they will the bonds will be polar. However, they will be symmetrically oriented along the central atom. So overall, they will cancel each other, and the molecule will have zero dipole moment or will become nonpolar. Same thing will happen in case of a tetrahedral. You can imagine that those two, for example, are pulling in this direction with an overall force in this direction, and those two are pulling in the opposite direction with the same force. So overall, the dipole moment is going to be zero on the central atom. Same thing for a trigonal bipyramidal shape. The two axial bonds will cancel each other, and the three equatorial bonds will cancel each other, and the molecule will be nonpolar. For an octahedral shape, each two of those will have an identical dipole moment in the opposite direction, so they will cancel each other. Those two will cancel each other, and those two will cancel each other. So overall, the molecule will be nonpolar. If you have a non-symmetrical shape, situation is going to be different. For example, in water, you will have a dipole moment running from the hydrogen to the oxygen, another dipole moment with an equal magnitude running along the second hydrogen-oxygen bond. However, those are not exactly opposite with respect to each other, so they will not completely cancel each other. And as a result, the molecule will have an overall dipole moment that runs in this direction here. The same situation will happen in case of ammonia. You will have dipole moments running along the hydrogen nitrogen bonds, but since these bonds are not completely opposite with respect to each other, they will have an overall dipole moment running in this direction. The direction of the dipole moment is gonna depend on the electronegativity of the atoms involved. Since fluorine is more electronegative than nitrogen, dipole moment is gonna run in the opposite direction, and the overall dipole moment of the molecule is actually gonna be also in the opposite direction with a smaller magnitude because the electronegativity difference in this case is much smaller than the electronegativity difference in the ammonia case. If you have any type of unsymmetry in the shape of the molecule that will cause the dipole moment not to completely cancel with respect to each other, the molecule is going to be polar. For example, BF3, you have three identical bonds around the central atom that are symmetrically oriented with respect to each other, so they will cancel each other and the molecule will be nonpolar. But if you look at Cl2CO molecule, clearly see that the dipole moment along the carbon-chlorine bond is different than the dipole moment along the carbon-oxygen bond. And as a result, those dipole moments will not cancel each other. And the molecule will have an overall dipole moment along this direction right here and will become polar. So any type of unsymmetry in the shape of the compound will lead to overall polarity in the molecule. Same thing if you look at this series of compounds here. For methane, the bonds are symmetrically oriented around the central carbon atom. So even if there is a dipole moment along each one of these bonds, they will cancel each other and the molecule will be nonpolar. If you replace one of the hydrogens with chlorine, you will clearly have a different dipole moment along the carbon-chlorine bond in comparison to the other three bonds. As a result, they will not cancel each other and the molecule will have an overall dipole moment along this direction and will become polar. If you replace two hydrogens with chlorines, different dipole moment along these two bonds in comparison to these two bonds, so they will not cancel each other and the molecule is going to be polar overall. Same thing here, three bonds with one type, fourth bond with a different type means it's not gonna cancel each other overall and the molecule is gonna be polar. If you have a tetrachloride with four chlorines around the central carbon atoms, these are four bonds of the same type. So even if there is any polarity in the bond itself, it's going to cancel each other due to the symmetrical distribution around the central carbon atom. Why we care about polarity? Because it actually controls the electrostatic interaction between molecules. It's going to determine the strengths of intermolecular forces, which will in turn affect the physical properties. The boiling point and freezing point of the molecule is going to affect the solubility and the reactivity of the molecules. And later on, we will discuss the different types of intermolecular interactions that arises between molecules, namely dipolar forces, hydrogen bonding, and dispersion forces. We will talk about these in details in the next set of slides.